Scientists achieved self-sustaining nuclear fusion. But now they can't replicate it. Scientists have confirmed that last year, for the first time in the lab, they achieved a fusion reaction that self-perpetuates, instead of fizzling out, bringing us closer to replicating the nuclear reaction that powers the sun. However, they aren't exactly sure how to recreate the experiment. Nuclear fusion occurs when two atoms combine to create a heavier atom, releasing a huge burst of energy in the process. It's a process often found in nature, but it's very difficult to replicate in the lab because it needs a high-energy environment to keep the reaction going. The sun generates energy using nuclear fusion, by smashing hydrogen atoms together to create helium. Supernovae, exploding suns, also leverage nuclear fusion for their cosmic firework displays. The power of these reactions is what creates heavier molecules like iron. In artificial settings here on Earth, however, heat and energy tend to escape through cooling mechanisms such as X-ray radiation and heat conduction. To make nuclear fusion a viable energy source for humans, scientists first have to achieve something called ignition, where the self-heating mechanisms overpower all the energy loss. Once ignition is achieved, the fusion reaction powers itself. In 1955, physicist John Lawson created the set of criteria, now known as the Lawson-like ignition criteria, to help recognize when this ignition took place. Ignition of nuclear reactions usually happens inside extremely intense environments, such as supernova or nuclear weapons. Researchers at Lawrence Livermore National Laboratory's National Ignition Facility in California have spent over a decade perfecting their technique and have now confirmed that the landmark experiment conducted on the 8th of August 2021 did, in fact, produce the first ever successful ignition of a nuclear fusion reaction. In a recent analysis, the 2021 experiment was judged against 9 different versions of Lawson's criterion. This is the first time we have crossed Lawson's criterion in the lab, nuclear physicist Annie Critcher at the National Ignition Facility told New Scientist. To achieve this effect, the team placed a capsule of tritium and deuterium fuel in the center of a gold-lined depleted uranium chamber and fired 192 high-energy lasers at it to create a bath of intense X-rays. The intense environment generated by the inwardly directed shock waves created a self-sustaining fusion reaction. Under these conditions, hydrogen atoms underwent fusion, releasing 1.3 megajoules of energy for 100 trillionths of a second, which is 10 quadrillion watts of power. Over the past year, the researchers tried to replicate the result in 4 similar experiments, but only managed to produce half of the energy yield produced in the record-breaking initial experiment. Ignition is highly sensitive to small changes that are barely perceptible, like the differences in the structure of each capsule and the intensity of the lasers, Critcher explains. If you start from a microscopically worse starting point, it's reflected in a much larger difference in the final energy yield, says plasma physicist Jeremy Chittenden at Imperial College London. The 8th of August experiment was the best-case scenario. The team now wants to determine what exactly is required to achieve ignition and how to make the experiment more resilient to small errors. Without that knowledge, the process cannot be scaled up to create fusion reactors that could power cities, which is the ultimate goal of this kind of research. You don't want to be in a position where you've got to get absolutely everything just right in order to get ignition, says Chittenden.